Okay, so this is the topic 7. It's actually the first part, but there's another part, the density. The curriculum that we're using for this didn't have anything on density, so it's going to come in a different format than you're used to seeing for the notes. But I'm going to go ahead and make the video for this first part, and so that some of you guys can get ahead if you were so desiring to do that. So similar solids, we're talking about similar shapes, so three-dimensional shapes. So it could be like a pyramid or a cylinder, something that's similar. So similar solids have exactly the same shape, but not the same size. Two solids are similar if the ratio of their corresponding linear measurements are equal. So the ratio is the first blank of their corresponding linear measurements are equal. So what we mean by linear measurements are one-dimensional measurements. So types of linear measurements would be like length. Okay, so maybe the 20 by itself is a linear measurement, or width by itself. So it can be height, it can be a base of a triangle or something. Perimeter is also linear, because perimeter just means the length around something. So really it's length, but it's just the length even after you turn corners. So perimeter is linear. A radius for anything that's circular is linear. Circumference, because it's really like perimeter is linear, and diameter. So diameter and circumference. So again, these are just things that are one-dimensional, so they're in inches, versus something that's two-dimensional, which is like inches squared. Okay, so we're talking about one-dimensional objects. Well, they're not necessarily an object at this point because they're just, they don't have any width. So directions for this first part, what we're going to do is determine whether the solids are similar. Okay, again, they need to be the same exact shape, but they could be different sizes. But their sizes need to be in the same scale factor. And then if yes, determine what the scale factor is in simplest form. So for each of these problems, we're going to be going from the first figure to the second. So if you write that from first figure to the second figure for each one. And our ratio, we can write it in ratio format, or we can write it as a fraction. But to determine the scale factor, again, we did scale factor, we've done it a couple times throughout the year, but you're comparing matching dimensions. So if you're comparing the height on this pyramid, then you would need to compare it to the height on this. So we would do 12 over 3. Okay, that would be the first dimension. And I just picked height to start with, but you can start with anything. Then if we compared the width on this one and the width on the corresponding side, which would be 2, versus the length and the length, so 20 and 5. Okay, if when you divide them, they're all the same, that's the scale factor, and they are similar because they have the same scale factor. So in this case, we get 4 for each of these. So our scale factor, if we were to write it in a ratio notation, it's simplified to 4. Really, it's over 1. You could really rewrite this fraction as 4 over 1. So our ratio is a 4-to-1 ratio. That means that this figure is 4 times larger than this figure. And the answer is yes, they are similar because they all have the same ratio, scale factor. Okay, for 2 and 3, you're doing the same thing. It's not super imperative that you find every side, but it is essential that you compare the sides that they give you. So all 3, if they give you 3, in this case they only give you 2, but compare things that match. So in this case I would be comparing the first figure, so 8, to the corresponding height on the second figure, so 12. And then one of the 6s to this 10, and the other 6 to this 10. Okay, obviously these two are going to have the same ratio, so we just really need to make sure that the 8/12 is the same as the 6/10. Okay, if you're not that great at simplifying fractions, then you can use this calculator. So again, to do that, we just do 8 over 12. Then we use the ABC button. I'm going to zoom out a little bit so that you can see. Turn this light off. Okay, so you have 8 over 12 as a fraction in your calculator, and then you would just hit equals, and it tells you what the simplified version of that is. So this is 2/3. Okay, 6 over 10 is 3/5. So already I know that since those are not the same, they have to be the exact same. Since those are not the same, this would be not similar. Okay, so they don't have a scale factor answer because this would be the scale factor of the heights, but this would be the scale factor of the sides, and they're not the same. Okay, so that's what we're doing for the first couple. On number 3, you're still doing the same thing, but they give you the diameter in one case, but the radius in the other. So make sure when you're comparing apples to apples. So you wouldn't want to compare a diameter to a radius. You would need to figure out either the radius on this or the diameter on this so you can compare it. All right. For the comparing volume to surface area, volume and surface area, when two solids, zoom back in. If two solids are similar with a scale factor of A to B, so they can have any scale factor, then their volumes and surface areas have the following scale factors. So surface area, so since surface area is two-dimensional, so it's got like centimeters squared, or feet squared, or kilometers squared, then we're going to need to square both the linear measurements to get the ratio of the areas, okay, because area is a square unit. Volume is a cubic unit, so we're going to cube both of the linear measurements to get the ratio of the volumes. So what that means for this first example on number 4 is if we're identifying the scale factors for each pair, all of these dimensions that they give us are each one-dimensional or linear measurements. So the 10 by itself, for instance, is a linear measurement. The 5 also is a linear measurement. So what we want to do is we want to figure out what our regular scale factor is, because linear measurements tell us the scale factor. So if we compare two things that are both the same kind of dimension, so like two heights or two bases or two widths, we would get 6 over 3 or 14 over 7 or 10 over 5. Okay, those divide evenly, so 2, which really can be written as 2 over 1, is the ratio for all of them. So if we were writing our ratio in colon format, it'd be 2 to 1. Okay, so following this format, if this is A and B, then the ratio of the areas, because we're doing every dimension is half of the size on this one than this. So when you multiply a half, and you're going to get a fourth of the times. But really we're going to use A squared and B squared. So that's going to be, we square this, we get 4. And we square 1 squared is still just 1. So the figure for similar solids, if the dimensions are all twice as big, the area is going to actually be 4 times as big. And the volume would be how much? What ratio do you think? Well, we would cube both the scale factors. So 1 cubed, anything, 1 times 1 is still going to give you 1. 2 cubed is going to give us 2 times 2 is 4 times another 2 is 8. So on your calculator, remember to use the cube. You're just going to do 2 and then hit second so that we can get to this green x cubed. So the 1 is so that we can get to this x cubed. So we're cubing the 2. So 8 is the answer for that. So the answers would be figures that have one side is twice as big as another side. The volume is going to be 8 times bigger, and the area is going to be 4 times bigger. Okay. It doesn't matter which one you start off to do the ratio with, so you could do 4 over 6. These are all similar solids, so these scale factors should turn out the same. So if we do 4 over 6 and hit enter, that's going to reduce to 2/3. If we do 7 over 10.5 and hit enter, okay, so it's not letting me do 0.5. So one way to get around that is to multiply these, well, you can just divide it. 7 divided by 10.5, that's the quickest way. And then that gave us a decimal, but we can just use our decimal to fraction button and say, okay, it's 2/3. So 2/3 is the scale factor because these are linear measurements. And this would be your A and your B. So if the linear measurements have a scale factor of 2 to 3, the area measurements are going to have a scale factor of 4 to 9. You square them both. Okay, so what we're doing here again is A squared and B squared. So we're squaring 2 and we're squaring 3. So 2 squared is 4, 3 times 3 is 9. And this one we're going to cube them both, the originals. So we're still using A, which is this. A is 2, so 2 cubed is 8, and 3 cubed. 3 times 3 is 9, times another 3 is 27. So those would be our answers for number 5. Okay, the next couple give you surface area or volume first, so they don't give you the scale factor AB. Might be doing too many of these. I'll just do one of these. Well, I might have to do 2, but okay. On number 6, they give you the surface area, so they start off giving you this. So 25 and 4, and they only give you the surface area, so that's actually. If you tried to simplify it in your calculator, it's just going to tell you that that is already simplified. Well, it gives you the improper fraction, but when you convert it to, it gives you a mixed number. When you convert it back to an improper fraction, it tells you 25/4 is the simplified version of this. So neither one of them are divisible by anything besides, well, they don't have the common factor, basically. You can't divide them both by 2, because this will give you a decimal. Okay, so this is your A squared and your B squared, because we're given the area this time, which is the squared dimension for each of these. So we need to get back to the A and the B. So if we have something squared and we want to get back to what just A was, even if we were doing like Pythagorean theorem and A squared equaled 25, then A would be the square root of that, so 5. And B squared is 4, so I'll write it this way. B squared is 4, so taking the square root, that means B is 2. Again, A squared was 25, so square rooting that, A is 5. Okay, you don't have to show this work, I was just kind of trying to explain it, but basically if you're given the square stuff, you square root to get the scale factor, and then you cube it again to get the volume ratio. So these are still A and B, so we're going to take 5 and raise it to the 3rd power, so 5 times 5 times 5. And 2 is our B, so 2 times 2 times 2, which we know is 8. Okay, so I'm not going to do this one for, well, actually I do need to go through this one. So A cubed and B cubed, because this time they give us volume. So if we put in 162 over 384, let's see what it simplifies to. So 2764 is the volume part. Okay, but this is A cubed, so A cubed is 27, B cubed is 64. To get back to A, we do the opposite inverse of this, so we cube root it. Now, we haven't talked about cube roots yet, but you did probably in algebra, but not in geometry. So the cube root, basically what that means is raising something to the 3rd power. We don't like that format, so we use the cube root. But if A, so I guess that's not, I don't want to confuse you, but you're just going to look for the function or the button that has a cube root, which is above the 0. So that 3 is supposed to be in the index here, so it's cube rooting 27. So if you take 27 and then you hit second 0, oops, sorry. I'll do it again. 27 and then hit second 0. It tells you that that root, what was cubed, what had to get multiplied by itself 3 times is 3. Okay, and if we do the 64, it tells us it was 4. Okay, you can do it, you can leave it in fraction form and do this. So if you did 27 over 64 and then just cube rooted the whole thing, well, it gives it to you in decimal form, but if you put it back in fraction form, it's 3/4. Then to get area, this is a and b, so we square it, and then we again have to change it back to fraction form, and it tells us it's 9/16. So if a cubed is 27, then we take the cube root to get rid of a cube. That's how you cancel a cubed. And then a was 3. We did the same thing for b. B cubed was 64. So we cube root that. And b is 4. So 4 is the number that if you multiply it by itself 3 times, you get the 64. That's what the cube root is. Okay, so a and b are 3 and 4. So when we square those, squaring this would give us 9, and squaring this would give us 16. Okay. So I'll let you try 8 on your own. Okay, this set is very similar to what we just did with 6 through the others, just a word problem. So solid A is similar to B, so that means they have the same scale factors for surface area, volume, ratio, scale factors the same. So the ratio of a height is given, and height is given. And then you're just finding the ratio of the volume. So it's actually no different than what you did on the first couple problems. I'm trying to find one that maybe requires slightly more work. Actually, these are pretty straightforward. I'll let you try them because it will show if you comprehend when to use cubed and when to square root things and what. Okay, so 9 through 12, I will let you try. Well, go ahead and try them, and I'm going to do number 12, but you can pause the video and just try to see if you can get it, and then just check your work. Okay, so pyramid A and B are similar. The pyramids have a pyramid A, so we're doing volume right now. That's the cubic measurement. Has a volume of 648, and B has a volume of 1029. What is the ratio of the surface area? So we have the A cubed, B cubed. We need to still get to the AB, and then we need to square it to get the area. So we go here and then back here. Alright, so to get 648 and 1029, okay, old school. So 648 divided by 1029 equals that number. So when I second, okay, so as a fraction, this is the volume. That's just changing from fraction to decimal, or decimal to fraction. So that's our fraction for the volume. So we still need to cube root that to get the fraction for the scale factor. That's it as a decimal. So then 6/7 would be it as a simplified fraction. Okay, then we need to square those. So then 36/49 would be your ratio for A to B, pyramid A to B. Okay. So again, if they give you the cube, then you cube root to get the regular. If they give you the regular, then you just square or cube it. If they give you the square, then you square root to get the regular. But you always need to get to the regular, then you can work your way to the other volume or surface area, whichever one they did not give you. Okay, so that's the first part. The second part, it's okay, this is just a recap of what we just did. So scale factor is just A to B, surface area is A squared to B squared, and then volume is A cubed to B cubed. Okay, so we want to reduce the ratio on these, and then we are going to write a proportion to solve for the actual volume. So this time they actually want you to figure out what the volume or the surface area or the linear measurement was. So let's look at a couple examples. So number one, if the cones below are similar, so they're already telling us they're similar, they have these ratios in common. What is the ratio of the surface area of the larger to the smaller? So we want the larger to the smaller. This is a one dimension, so it's just yards versus yards squared or yards cubed, so I know that this is the scale factor. I do want to figure out the reduced version of that, so 28/8. If you don't have one of these calculators that does this part for you, unfortunately it's going to be a little bit more work, but you're just going to basically figure out what number divides evenly into these. So I know that 4 goes evenly into this 7 times, and it goes evenly into this twice. So when I hit enter, well, it gives me the mixed number, but if I go to improper fraction, it tells me 7/2 was correct. So you just have to do that part yourself if you don't have a calculator that does that. But that's the scale factor. So I haven't actually done any work yet. I just simplified this fraction. And so again, if I had 28/8, those are both divisible by 4. So I would end up with 7/2. That's just the scale factor simplified. All right. So then we want the area. Surface area and area are both square dimensions, like 2-dimensional. So we're just going to square these. So 49 and 4 would be our, actually that's all we have to do for that. It's just ask for the ratio. That would be our ratio. Okay, I'm looking for one that doesn't say ratio. What's ratio? Okay, all the front page is all ratio. So they don't care about the actual height, they just want another ratio. So it's just like the problems you just did on the other worksheet. Okay, so 7 is actually where they start to use the proportions. So on this one, the ratio of the dimensions of a diameter, okay, this is diameter is 1-dimensional, so it's in like inches or feet or whatnot. So it's 3 to 5, so that's just your scale factor. If the surface area of the smaller cylinder is given, so they're giving us actually the surface area of the smaller cylinder. Find the surface area of the larger. So what we need to do first is find the ratio of the surface areas. Then once we have the ratio of the surface areas, we are going to use proportions to find the actual surface area. Okay, so again, if our scale factor is 3 to 5, our ratio for surface area is going to be, this is A and B, so we square A and square B. So 9/25 would be our surface area ratio. Okay, so 9/25. Then we want to use proportions, and this is one of our sides. So 9/25 would be one side of our proportion. And then they tell us that the smaller area is 378. So this is really important that you put the 378 in the correct spot. So it can go in either one of these, but since it's the area of the smaller, we would put it with the smaller number, so you put it in line with the 9. And then x would be on the denominator in this case. Okay, at this point we're just cross multiplying to solve. So 9 times x is 9x. 25 times 378 is, sorry for such a glare, 9,450. And now we're solving like a regular algebra problem. So x is equal to, dividing both sides by 9, 1050. Okay, so 1050 would be the surface area of the larger cylinder in square inches. You can kind of know if you did the setup for this right is if your larger cylinder's surface area is larger. It should be larger if it's the larger cylinder. So use blank to set up the proportion. Okay, use the ratios. But you don't need to keep writing that. But that's the process. So you're gonna start off with two things, maybe a scale factor, and then one dimension on the actual dimension on a pyramid for volume, and you have to find the other one. So again, you're going to find the ratio of whatever dimension you're eventually looking for, which in this case is volume. Then you're going to set up a proportion using the ratio for volume and the actual volumes they give you. Okay, so I'll just let you do 8, 9. I'll do that one. Okay, so they give us the volumes for both of them. So instead of starting on with surface area, because I mean SF scale factor, we don't know the scale factor for these, so we want to use the volume ratio. So 840 to 105. And we can see if that simplifies. So 840 to 105. It's exactly 8 actually, so this is not, this one's not, it doesn't end up being too bad. So 8 to 1 is the volume ratio simplified. So I crossed it out so that you can see that these are really the same thing, just one simplified version of the other. Okay, so then that means our scale factor should be what? Okay, volume is a cubed, then a is the cube root of this. So we take the cube root of 8, and the volume, sorry, the cube root of 8, so that's a 3. So that's 2, and the cube root of 1, which anything, for 1 it's just always going to be 1. So the scale factor from this figure to this figure is 2 to 1. So some of you will be already able to tell, since this is twice as big as this other figure, what x is. But if not, then you would set up your proportion here. 2 to 1, which is the ratio of the scale factors, is one side of the proportion. And then the other side would be the dimension that you know, which the 20 is on the bigger one, so I put that with a 2, and then x. So when you cross multiply, you get 2x equals 20, or x is 10 centimeters. Okay, so try the other ones, check the answer key, make sure you're killing it on those. And we have one more little page on this one. Okay, so effects of changing dimensions. So if the dimensions of a solid are multiplied by a scale factor, let's say a, then the surface area is a squared times the original surface area, and the volume is a cubed. So it's really kind of the same thing that we've been doing, except for it doesn't have the b part. So if the dimensions of a figure are doubled, how many times larger will the surface area be? Okay, so the dimensions of the figure, which means the linear dimensions, are doubled. So a is originally a, and it's doubled, so it becomes 2a. How many times larger will the surface area be? So if we get rid of a, our ratio is 1 to 2 essentially. So the surface, and that's scale factor. So the surface area should have, we should square this. So 1 to 4 ratio. And it just says how many times larger, so we would just say 4 times. We don't want the ratio, we just want how many times bigger this is. Okay, so we'll do a couple more of those together. Okay, so number 3. The surface area of a figure is 736. If the dimensions are multiplied by a fourth, what will be the surface area of the new figure? Okay, so we can go about doing this a couple different ways. The first way would be to use the scale factors and work backwards for the proportions. Or we can actually use this number and divide it by, it mentions them multiplied by a fourth. Actually, we do have to go back. We have to use the original way. So if they had given us the linear dimensions first, we could do both options. But so let's say the surface area of the figure is 736. So we want to know what would be if the dimensions are multiplied by a fourth. And that's the dimensions, that's like the linear dimensions. So basically, a is a fourth of the size. I can just write it like this. So this is 4a and this is a. It's basically getting smaller is what the fourth means. So it's a 4 to 1 ratio for this dimensions. And the surface area ratio would then be what? Okay, 16 because it's a squared and 1. Okay, so then surface area is 16 to 1, and the original surface area was 16. So 16 to 1 is now 736 to x. Okay, so this will become 16x equals 736, and when I divide them both by 16, I get x equals 46 square inches. So they told me the dimensions are multiplied by a fourth, which really means like the linear dimensions. So like each of the base might be multiplied by a fourth and the height might be multiplied by a fourth. So really they're telling us scale factor here. Yeah. And then we go back from scale factor to surface area ratio, and then we can use our proportions. The actually other way to do this is to, I mean, I'm not sure which one would make more sense to you. I was trying to figure out in my head which one's kind of easier. If we square root 736, that would be the, if we square root 736, that would be basically the linear dimension for the first figure. And then we want to multiply that by 1/4, so timesing that by 1 and dividing by 4. The new dimensions are going to have this as one of its linear dimensions, so 6.7. But then we would need to square because we want area. So we get back to the 46. But I'm not sure. Yeah, whichever of those makes more sense. So you can square root this to figure out what the actual linear dimension of the figure was. Let's just say it was a square. A square. So it's base times height, but they're both the same. You would just square root this to get the linear dimension of one base. Then you multiply by a fourth, so you make it a quarter of the size, and then you square that back to get the new area. But I think this makes more sense to do it out. So okay. Okay, and then volume examples. So those are just surface area. So volume is similar, but it's just the cubic dimension. So if we look at say number 6. So the volume of a figure is given if dimensions are doubled. So the dimensions are the linear dimensions. So the linear dimensions are doubled. So it's in a ratio of 1 to 2. So we want to figure out what the volume's effect is for the ratio and then put that in proportion with the volume they give us. So if the scale factor is 1 to 2, what's the volume ratio? We would cube this and cube this, so it's 1 and 8. Okay, so the volume has a 1 to 8 ratio, and the volume of the figure originally was this. The new figure is going to be bigger because the dimensions got bigger. So this 110 goes here, and this is x. So 110, well, let me show you on here. 110.5 times 8 gives me 884. So the new volume would be 884 cubic feet. Okay. Let's do 7 because it has a fraction in it. So the volume of a figure, okay, they give you the volume, but the dimensions are multiplied by 2/3. So that means the smaller one's actually, the second one is actually smaller because 2/3 is less than 1, so it's getting smaller. It's like 66% of the size. So really this is a 3 to 2 ratio because yeah. Okay, because even when we did, like, let's say we did the 4 to 1 ratio, really we put the 4 because it's bigger and the 1. So fraction here, we just knew 4 is 4 times bigger than 1, but we actually are using the ratio 4 and 1. We're just putting it in reverse order. Same thing with doubled. Doubled usually means 2 times the size, so we put the 2 back because it's getting bigger. All right, so 3/2, 2/3 just means 3/2 basically, because the figure went from a bigger figure to smaller. So that's the scale factor. The dimensions are multiplied by 2/3. So the volume's scale factor ratio is going to be 3 cubed. So 3 times 3 times 3 is 27, and then 2 times. These 3's are supposed to be exponents. They're drifting a little bit. Okay, so that's the volume ratio. So we're going to use 27 and 8, and a figure has originally 972. So even if you jack this up, as long as you realize the figure got smaller from 2/3, then you just can put the 972 with the smaller of these two. Okay, so 8 times 972. so we just cross multiply and solve here. Alright, this video is getting on in length, so I'm just trying to see. The back is a little bit different, so I didn't get to go through the back. Just a couple examples probably. Okay, so changing only one dimension is different than changing all the dimensions. So changing only one dimension means that the figures they're not similar anymore. So they're not similar. Therefore, we need another strategy. So in this situation, we want to choose. Actually, I don't really choose test values, but that was what originally her notes had. So I'll put it on here. I don't really do it that way, but I'm just lightly running through it. So basically, the strategy would be to use the formulas for those particular objects and then only double the dimension it tells you. So for instance, on number 9, how many times larger is the volume of a cylinder if the height is doubled? So the volume of a cylinder originally is, okay, so the volume of a cylinder, capital BH, since this is a type of prism, it maintains thickness, where the B in this case is a circle. So this is kind of a good review for the formulas. So the circle is the base shape on a cylinder, if I redraw it. And then I would be taking that times the height. How much does it take to fill it up? So the area of a circle is pi r squared, that's what the shaded part is, times the height. Okay. If we only double the height, we want to know what the effect is on the volume. So the height is just one dimensional. So if we only double one dimension on this, then the volume, it should only be doubled. So we just double one. So essentially, this is the original old. So volume for the old. So the volume of the new is going to be pi r squared, and then the height is doubled, so it's 2h now. So if we bring the 2 to the front, it's 2 pi r squared h. So comparing this and this one's just twice as big. So 2 times bigger. Okay. So basically, whatever dimension, if you were to double the height and it's only one dimension in the equation, then the volume only gets doubled. If you were to double the radius, though, since it's 2 dimensions and it's radius times radius, then the height would get, the volume would get 4 times bigger. So let's just do one more of those together. Let's see, triple to half. I'm looking at the computer to see how small is the surface area of the cube. Okay, we'll just, I think they're all the same after it. Locked me out. Okay, so let's do number 11, or 12. How many times smaller is the surface area of a cube if the side length is multiplied by 4? So, surface area of a cube is a kind of rectangular prism that has all the same sides, all the sides the same. So, but the surface area for a cube is, okay, so the base, so like, let me just draw it out. So the base and the height are the same. So the base is the base here, and the width is also the same. So all of the sides, and there's 6 of them, have an area of b times b. So your surface area for a cube is going to be 6b squared, which b stands for just one side. They're all the same on a cube. And then if how many times smaller is the surface area of a cube if the side length is multiplied by 4? So the b is, in the new figure, is 1/4 of the size that it was. So 1/4 of b squared. Okay, so we're basically squaring the 1/4 and the b. So this is going to become 6. If we square 1, we get 1. If we square 4, we get 16b squared. So everything is the same in the formula, so 6b squared is still there, but it's divided by 16ths. So how many times smaller is it? 16 times smaller, because it's a 16th of this original, which is understood to be over 1. So this one's over 1, this one's over 16, so this is 16 times smaller than originally. And when you're squaring things, you just square everything individually. So you square 1, and that gives you 1. You square 4, and that gives you 16. And you square b, which gives you b squared. Then all of these things are on the numerator, so you can multiply 6 times 1 to get 6, and then b squared is still up there with that, and then all of it's divided by 16. 6b squared was originally in the problem, so it's 16 times small. Okay. I'll let you guys figure the rest of that out. And if you have questions during our time together on the group chats, on the team meetups, then you can ask me then.